can you all hear me okay?
Yeah.
Okay. So I kind of want to just continue our discussion from lab today. So this morning I introduced the concept of induced EMF. And conceptually, to me conceptually, these are not, this topic is not easy to understand. If you look at it, at a kind of a superficial level, it looks okay, but if you start digging deeper, it starts getting confusing. I've always noticed that. So since I have a little bit of time, I did want to clarify something about the work done in this particular case. This is based on a slide that's in your notes, but the slide has a couple of mistakes in it, so I will send you the correct version of the slide. Okay. Just as a reminder, these are your next assignments that are due, and exam 4 is on May 4th. Okay. All right, and I will try to do some demos today. We'll see how far we get.
We got a few questions in the chat.
Oh, I'm sorry. What is the EMF? The EMF it's called the electromotive force. I know it's not the greatest term that's used, but it's basically an induced EMF, induced voltage. Okay. I mean, it's just an induced voltage. And the reason why I use electromotive force really is because, I mean, I guess one way to think about it is because this is due to the motion of either the motion of circuits, well, in this particular case, it's called the motion of circuits, or a changing circuit. So we use that term. Although that term is also used for batteries, which is not a good term. Okay. So I want to go back to the discussion this morning regarding the rails and the bar. The bar was moving to the right, magnetic field into the board. And so let's assume now the electrons are moving because of the fact that the rod's moving in the electric field. And what I drew here is the velocity of the rod, and then really the velocity of the electrons relative to us. Because the rod's going that way and the electrons are moving down, their total velocity looks like this. In fact, the velocity of the electron is the velocity of the rod plus their drift velocity. And then I drew this angle theta, so that the velocity of the rod can be written as v electron times cosine of theta, and v drift can be written as the velocity of the electrons in our frame times the sine of theta. Okay. Then I looked at the force on the electrons in this. Because the velocity of the electron is in this direction and the magnetic field is perpendicular to the board, the force on the electron has to be both perpendicular to the velocity vector and the magnetic field vector. So the force is this way, and if you want to, you can use the right-hand rule to verify it, or use the cross product. But the force on the electron is in this direction. And it has two components, one pointing downward, which actually moves the electrons downward, and then one that points to the left, which represents the force on the bar due to the moving charges. So F electron cosine of theta, FB cosine of theta is the force on the electrons in the rod. And F sub B sine of theta is really the force on the rod. And so
is that a negative in front of the velocity of the electron sign for V drift?
Yes, that's a negative.
Okay.
Hold on a second. Okay, I'll make it. Is that better? Or I'll make it bigger.
Yes, that's better.
Okay, all right, there you go. So, FB is F cosine of theta. I'm sorry, F electron. This is FB cosine theta. Now F sub B, I'm running out of space. F sub B is just Q, the velocity of the electrons, times the magnetic field. And so I wrote that here, and then multiplied it by the cosine of theta. But V of the electron cosine of theta is the velocity of the rod. So the force on the electrons themselves is Q times the velocity of the rod times B. The force on the rod then is F sub B sine of theta. So the force on the rod is Q times V electron times sine of theta. Okay. What I want to do is calculate the work done on the rod and the work done on these on the charges in here. So the work done on the electrons is the force on the electron times this distance. Let's say they move through this distance. Okay? Then force on the electron is going to be given by this expression. I'm sorry, this expression, Q V rod B. So I put this here and I get Q V rod B times L. So this is the work done on the electrons. It's given by this expression. Now, this doesn't necessarily say that there's a work done by a magnetic field. All it says is the relationship between the work done on the electron and the values that are given. Let's look at the work done on the rod. Because the work done on the rod, let's say when the electrons go from here to here, the rod travels a certain distance this way. How do we figure out the distance the rod travels horizontally if the electrons travel a distance L? Well, here's a picture of the velocity vector for the rod and the drift velocity for the electron, and this is the total velocity of the electron. V rod over V drift is cotangent theta. Does everybody agree with me on that? Mm-hmm. Let's let T be the time it takes for the electron to go from the top to bottom. Okay. So this distance is L, right? Mm-hmm. So let me say it's V rod times T over L equal cotangent of theta. So then V rod times T, which is the distance this rod moves horizontally, is L cotangent of theta. So the force on the rod, which is right here, times L cotangent of theta, gives me the work done on the rod. Or the work done, or this is the force you have to apply on the rod to make it go at a constant speed. So you have this, Q V electron times B times L. This is cotangent. Sine of theta, cotangent of theta. What's sine times cotangent?
Cosine.
Cosine. So you get V electron cosine theta, that's V rod. So the work done on the rod is Q V rod B times L. So the work done on the rod is the same thing as the work done on the electron. So if you push the rod and you do this much work on the rod, it's going to do this much work on the electron. So the work is done because of the fact that you're pushing the rod with some force. And we're pushing the rod so that the rod goes at a constant speed. Okay, so that's where that comes from. And that illustrates that it's the rod doing the work on the system. And I have a slide in there, and I'll send you a better set of notes. This vector for some reason was down here and this vector was up here. I'm not sure why I did that. Okay, so I have to fix that. I mean, I fixed it already. I just got to send you the new set of notes with that correction in it. That's the only correction I have. Okay. Questions on this?
So we are saying that there is a component of F sub B which which acts as a force on the electron on the downward side, right?
Yes.
So does that increase its velocity in that rod?
No, because as these separate, there's an electric field that's developed, right?
Okay, so that is keeping it constant.
Well, yeah, that'll keep it constant.
Okay. Mm-hmm.
Because these charges will accelerate in the vertical direction until the force due to the magnetic field equals the force due to the electric field.
Mm-hmm. Yeah.
Okay. So when you look at textbooks, in every textbook, they just say, okay, the electrons move down, but they don't do this kind of analysis because they're trying to keep the analysis more superficial. But now when you start thinking about it in a more deep fashion, you actually have to say, oh, the velocity of the electron is not really downward, but it has a component to the right too. You see what I mean?
Mm-hmm.
So it does get more complicated the more deeply you delve into the topic. Okay. And in fact, I think pretty much every textbook, there's no textbook that I think describes it this way. And I think the first paper that I saw that talks about this, there's papers on teaching physics. They say, why aren't we talking about it this way? And it was like in the 1970s. And the textbooks still ignore this. Part of it because they're worried about causing confusion, I'm not sure. So I just wanted to introduce that. I just wanted to show you that since we have a little bit of time. So I want to do a couple of examples now. Really talking about Lenz's law, motional EMF, etc. Suppose I have an airplane, or suppose there's an airplane flying horizontally at a constant speed above the Earth. Let's assume that the magnetic field that the plane experiences is uniform, just to make life easy for ourselves. Okay? And so it experiences a uniform magnetic field. It could be, we'll make it into the board. We're looking above the plane. I didn't put any tail to the plane, but that's okay. Let's say the plane's going that way. Okay? What's going to happen? But I mean, there's charge. This is made out of metal, right? The airplane is constructed out of metal. What's going to happen to the charges in the metal? For example, what about this part of the plane as it's moving that way? What's going to happen to the charges?
The negative charge will go to the right side of the plane, like Damien said.
They would go to the right side of the plane. So the force will be in the same direction as the velocity vector. Shouldn't the force be perpendicular to both V and B? Oh, in the wing. So the charge.
Yeah, on the wing.
Okay, so the charges will redistribute themselves. So let's use the right-hand rule. So magnetic fields into the board. V points in this direction. V cross B is up, but the electrons move downward. So you're going to have negative charge here plus positive charge here, right? Something like that. So this is going to be positively charged. This will be negatively charged, right? And
Yeah.
will you have a current? Will there be a current there, or are you just going to get a separation of charge? Is this just like the Hall effect? The answer is yes. You're just going to get a separation of charge, and that's it.
Yeah, because there's nothing for the current to flow through.
Yeah.
Say that
Right.
again.
Just because there's no
You're absolutely correct. Because we don't have a closed path, you're not really going to have a current. Okay. And is this flux changing across its wings?
no, because there's an equal amount of magnetic field on both sides of the plane, right? It's not like more of it's being closed by the loop.
Yeah, so there's no changing flux. Okay. And so the EMF is induced because of this. Let's try
Right.
another one. Let's say we have a loop of wire of fixed geometry. So let's say a rectangular loop of wire, and I gotta find my eraser. So I'm gonna be asking you guys some questions for a little bit here. Again, let me draw my magnetic field. I won't draw as many, I'm going to stop after this row. I'm going to spend my time drawing X's. And then let me draw my loop. I'm going to draw a rectangular loop in this uniform magnetic field. And let's say these are infinitesimally, these are really thin wires, okay? And let's say that the the loop is moving to the right with some speed v. Is the flux changing through the loop?
Still no.
No, so the flux is not changing here, right? Uniform magnetic field. Now, granted, if the field was not uniform, that would be a different case, right?
Right.
You would just have, and it would be easy because as long as you know a magnetic field here and a magnetic field here, okay, you can actually very, very easily calculate the induced EMF for the whole loop. How is the EMF induced in this particular case? Because there's an EMF, right? Where's the EMF induced here?
Is it only?
Go ahead. I'm sorry.
Is it only on the left and right sides?
Yeah, only on these two sides, right? So isn't it true that the induced EMF on the left and the right? Let's call this, I guess we'll call it, what do you want to call this height? I guess L? Or H for height. They're the same, right?
Mm.
Is there a current in this loop?
I don't think.
Yeah. No.
There's no changing flux, right? There's no current induced because the potential difference here and the potential difference here are the same, right? Mm-hmm. These two points and these 2 points are at the same potential. Mm-hmm. So if you integrate around the loop, you essentially get zero. Okay. So yeah, you don't have a changing flux. You actually need the changing flux in order to have that current in the loop. So let's try this one. I have a wire carrying a current. I'll use green. I have a wire carrying a current to the left. I don't know why it's black and green, but and then I'm going to put a loop above it. What if let's let di over dt be greater than 0? Is there a changing flux in that loop?
Yeah, because the magnetic field is changing.
Because the magnetic field, not only is it changing, but as you go further away from the loop, the magnetic field decreases, right? It's changing in time, and its value is different here than here.
Right.
Okay. So having said that, what is the direction of the induced current? Okay, I see a question by Chase. I induces the current induced in the loop by the outside wire. Yes. This is going to charge the flow in this wire. Because you have a changing flux, because you have a time varying magnetic field, you actually don't need this loop of wire for the electric field that's induced to exist. Okay, all this wire does, it allows the electrons in here to experience the electric field, and they're going to move around the wire. So which way is the current going to flow here?
Clockwise?
So you're saying that the current will flow this way?
Yeah, I mean, I think so.
Okay, so let's see. So I just want to check for consistency. So if I use the right-hand rule, the magnetic field here is into the board?
Right.
Okay. And we just want to check, right? So I guess I don't need to do all those X's. So the magnetic field is increasing into the board. What does Lenz's law say?
There's got to be a force exerted out of the board, or a magnetic field out of the board to compensate.
Yeah, so if I use the right-hand rule on this piece, right? If they have the magnetic field coming out of the board through this loop, shouldn't my thumb point in this direction?
So is the current on the wire going to be based on the direction of the induced field and not just on the one that's there?
Which wire?
Well, I mean, if the charge is flowing that way on that wire, the closed loop.
Okay. The current that's going to be induced is going to depend on the direction of this guy, basically the magnetic field going through the loop, and whether the magnetic field is increasing or decreasing.
Right. Well, what I was saying is because if you use the right-hand rule with the field into the board, doesn't it need to go clockwise?
The field is due to the outside wire. That has
Right,
to
but
be.
the field is into the board, though.
Right here.
Yeah.
Okay. But you need to induce a field that's out of the board.
Right. So I'm saying that the direction of the current is going to be based on the induced field, not the field from the other wire.
Yes.
Oh, okay. Well, then yeah, it'll be the other way.
Okay. Okay, so the current's going to go this way.
Is it similar to the solenoid one that we did?
Yes.
Okay.
Right, because the electric field was circulating in the opposite direction, right, of the current in the solenoid, wasn't it?
Yes.
Okay. And so what I was trying to do with that problem is do an example, then, but also allude to Lenz's law. And by the way, I have and I didn't caption it, unfortunately. I have on in the modules that a video of that problem where I go through all the details. I go through in a lot more detail. So if you're concerned about some of the details in that problem, I'm hoping that the video will go through all of them, because the books a lot of times avoid some of the details. You know, how do you know the direction of the induced electric field? You know, students will ask that question. The book really, they just say, oh, well, because of symmetry, it'll be this way. This is a demo I usually do in class. I was going to try it, but the fuse on one of my devices, I brought the device home, but the fuse was blown. So if I get a chance over the weekend to get the fuse, I'm going to try this. Okay. So suppose I have, and maybe I'll blow this picture up so you can see it better. An electromagnet connected to a DC power supply. And I close the switch. What's going to happen? Now, at the top, you see that red thing at the top? Mm-hmm. That's just a ring that you put at the top. So let's say you would put something like an aluminum ring. You put an aluminum ring like this at the top of that magnet. Okay? Like I said, I was going to do it. I was going to try it, but I have a blown fuse. First of all, what happens when you close that switch?
Current flows.
A current flows, because you have a current that's flowing, you have a magnetic field. Mm-hmm. You have the magnetic field go from 0 to some value, so you have a time varying magnetic field. Mm-hmm. Now, this is a conductor. And so this conductor is going to experience a changing flux. And there's going to be induced a current in here around the azimuth of the ring. That's going to produce a magnetic field that opposes the magnetic field of the electromagnet. Guess what's going to happen if the field is big enough?
Reverse the current.
Well, what happens to the ring?
Would it be pushed away?
Yeah, in fact, you would get something that happens like that. If the force is big enough, then what will happen is you're going to have two magnets that want to repel each other. And the ring, if the force is big enough, the ring, if you can overcome the weight of the ring, it'll actually lift off the ground. And so that's what I do in the classroom. I do it in S111 because usually the ring hits the ceiling. Okay. All right, almost hits the ceiling, but when I dump it in liquid nitrogen, it can actually go higher than the ceiling in that room. Okay. And if I do it here, I'm going to have to be careful because I don't want to mess up my ceiling. So that's an interesting example of Faraday's law. Now, what happens if instead I do the following with the ring? Let's say I give you a ring that has a cut in it or a slot in it. I use this in that magnet. Like you see in the figure. Let's say I put a slot in it. What do you think is going to happen?
It's not going to slow down because there's no loop for the current to flow.
Yeah, you're essentially going to get no current to flow, and so nothing will happen to the ring. The current that is induced in that ring is called an eddy current. Eddy currents are not wanted in motors or transformers because they produce heat. They waste energy, especially in transformers. They allow the transformers become less efficient. Okay. Now in a transformer, what you can do, I'll give you an example of what a transformer looks like. It's really heavy, so just give me a second. I got to pick it up. So here's my transformer. It's 2 coils, and this is pretty heavy, with an iron core around it. This iron core would get really hot if I was running it, because of the fact that I would dissipate a lot of heat in the iron core. And so what you do with the iron core is, and it's really hard to see, you can't see it here, but the iron core in here is actually sliced into thin sheets and then glued back together. That increases the resistance in the iron core and reduces the eddy current losses. So let me show you a couple of examples of eddy currents. And I'm hoping you can kind of see this, so I'm going to have to zoom in. Maybe I don't have to zoom in. So I have here is a rod. I'm going to move back. I tried to choose a rod that wasn't that tall. And I'm going to drop a little ball. This is just a little steel ball. And you'll hear it when it hits the ground, okay? Did you see it bounce up?
Mm-hmm.
And how long did it take for it to go through the tube? This is a copper tube. It went through it pretty quickly, right?
Yeah.
Okay, instead of using a ball, I'm going to drop a magnet. Well, here we go. I'm going to take the magnet and drop it. I'm going to wait to catch it. I'm still waiting. Oh, there it is. What happened there? Why did it take so darn long for the magnet to fall? Why did it take so darn long for the magnet to fall? The ball went through real quick, right? Why did the magnet take forever? Well, what do you think the tube is experiencing? Yeah, and it's an induced EMF. This magnet falls, and the tube experiences a changing magnetic field, just like in the example with the jumping ring. If you go online and just type jumping ring, you'll see all the demos. So same thing, you're going to get an induced current around the tube. It's going to act like a magnet. That magnet is going to provide a resistive force on this falling magnet, and it's going to fall through very slowly. It'll quickly reach terminal velocity and fall very slowly. When these labs are on campus, they're easier. See, I actually use a much longer lab tube on campus. So you should look under the jumping ring. Just type this.
We can't see up there.
Oh, sorry. So you got to type jumping ring demo. And usually the other one's called a lenses law demo. If you do these searches, you'll find them. This one's cool, but it's hard to do this at home. Okay, the other one is, you can do, but it's a little bit harder to do. So I want to do one more demo on eddy currents. Okay, let me change the camera. Maybe zoom in. Whoops. You guys see that okay?
Mm-hmm.
So you see here, just so there's no tricks, this is just a swinging aluminum pendulum. And it's not magnetic, so let me grab this magnet. The magnet doesn't stick to it. Okay? It's not magnetic, it's aluminum. Okay. Now watch this. I'm sorry? What I'm going to do is let this thing swing in the magnetic field. So let me do this again. So it swings by itself nicely. I'm only put it in the magnetic field. How many oscillations? You see how the magnet just completely stops it? It stops it dead in its tracks. Can you imagine, can you think about developing a braking system using this idea? I mean, there are systems that use this for braking. Now, if I change my paddle so that the bottoms are cut out, okay, oops, can't see it, sorry, so that the bottom is cut out, so just so you see the difference between them. So there's one, there's the other one, okay. Let me use this one. Because the resistance is higher, it's harder for the current to flow. It takes longer to stop. And so the eddy currents just flow around here as it passes the magnetic field. And that causes the braking. It causes it to stop. And so braking systems use this idea. Your electric car, if you have an electric car, it does use Lenz's law. Anybody have an electric car? Anybody drive a Prius?
So is this kind of like a basis for like an energy recovery system for
Yes.
braking?
So that's what happens when you brake on the in the Prius, right?
Yeah.
They have a regenerative system. I have a Volt that has the same thing. So it's using Lenz's law. I've hold on a second. You really get to see the effect of the regenerative system when you come down from Donner Summit. You start going down Donner Summit, you just let it coast, and you'll see the number of miles left on your charge go up. Some cases as much as 10 miles as you're going downhill. I mean, you can really see the effect. It's amazing. So eddy currents, in some cases, are not wanted, but in some cases, they're very useful. Here's another interesting little problem. There is a wire, a long wire, along the diameter of a ring. A long, thin wire along the diameter of a ring. The current in the wire is increasing. In which direction is the induced current in the loop? Oops. What do you think about that one?
If it is in certain direction, then it is going to increase the field in one half and decrease in the other. Like if we do have a current, and that does not look something that should happen.
You're saying there shouldn't be a current?
I mean, if there is a current, it looks like it is going to increase in one half. The field is going to increase in one half and decrease in the other.
Oh, so what's the total change in flux over the whole loop?
Nothing.
Nothing. So what does that mean then?
No current.
No current. Nothing's going to happen. Right? That's an interesting geometry. So that's a system where you're not going to get an induced EMF at all. You're not going to get any current at all, because no matter what you do, the total flux through that loop is going to be zero. As long as it's, along the diameter, of course. Right? As long as that wire is along the diameter of that green ring. You okay with that?
Yeah.
Okay. Let's try this problem. So you can see I'm just doing a bunch of examples right now. Suppose I have a long current carrying wire, and I changed the picture because I was for many years I was using the same picture as one of the problems from chapter 29, which was really not right. So I changed it to this. So again, I'll email you the new version of the notes. So I have a current, a wire carrying current. I'll use a different color for the wire. And I have a loop below it. This is D. D plus A. Let's pretend the current varies with time. Let's assume the current is time dependent. It just varies with time. I want to calculate the induced EMF through this loop. Okay, so again, Lenz's law. Whether I use S or L here doesn't matter. I want to calculate this integral. This one's going to be hard for me because I don't know what, I'm going to have a hard time calculating the electric field. But this one shouldn't be hard, because what does the magnetic field do to a wire? Oops.
Mu naught I over 2 pi. I don't know.
Yeah. This is the equation. And so I'm going to call this the y direction. So I'm going to call this y. because the distance from the wire is y, right? Remember, this is a distance. This is not a coordinate. Okay. So B dot N. Of course, I'm going to choose, what surface am I going to choose? I'm going to choose the planar surface. I can choose any surface enclosed by the loop, okay? I can choose any surface I want that's enclosed by this loop. Right? Because you're integrating electric field around the loop, and it's equal to the time derivative of the magnetic flux through that loop. And I don't care what surface I choose. Okay. And actually, this was actually pretty easy to prove to you, and if I have time, I can show it to you, that it doesn't matter what surface you use. It's pretty easy to prove that. Okay, I'm going to choose the normal in the direction of the magnetic field. Which direction is the magnetic field in this loop?
Into the board.
It's into the board. So I'm going to say, since N is into the board, since B into board, choose N into board. What that means, though, is if I were actually to do this integration, then I would choose my ds so it's consistent with my N. So if I integrate into the board, then I would actually, my normal's into the board, I would integrate around the loop clockwise. Okay? Because my fingers would go clockwise when my thumb goes into the board. Just to be consistent, otherwise you're gonna have to deal with negative signs. So the magnetic field does vary with distance. So my dA, I have to do an integration. I have to actually break up this rectangle into small strips in this direction. I want to make this strip thin enough so that the magnetic field is uniform over that strip. So my dA is LDY. Okay, I need to break up the strip into pieces small enough so that the magnetic field is uniform over that strip. That's the name of the game. Okay, so, and we've done stuff like this before. Same kind of mathematical techniques as when we talked about determining the element of charge, etc. Okay, so I'm choosing these two to be parallel to each other. So the dot product between these two is just going to give me this expression. And so my induced EMF is going to be the integral of B dot dN and I'm going to just choose this way as positive. So I'm going to integrate from D to D plus A. And so this is going to be minus d by dt. What's the integral of this thing? What's the integral of dy over y?
Natural log of y.
Okay. So it's going to give me the natural log. And when I take the derivative, the only thing that varies with time is the current.
Where did the L go?
Okay, right there. Okay, thank you.
Okay.
There's the L again, okay. Because I forgot it twice. Now, where was I? There you go. The minus sign just has to do with Lenz's law, right?
Why are we writing I twice?
Because I screwed up. Okay, there. Is that okay?
Yes.
Okay. It's always harder to write on the board. What is the direction of the current? What's the direction of the induced current here? Well, I got it. What do I have to tell you? Let's say di over dt is greater than 0. What's the direction of the current?
Counterclockwise?
Let's see. The field is into the board. The current is increasing. So you want a magnetic field out of the board, right?
Mm-hmm.
So you want a current this way. So it's going to circulate counterclockwise. That's right. Okay. If di dt was less than 0, then the current would be clockwise.
Mm.
Well, this is a classic problem that's in your book. It's one of the few problems you can do. There's not a lot of problems you can do where you can carry out this integral nicely. You know, you get a nice answer to this integral, an analytical form. So let's go back to our the rod moving on the rail problem. Suppose I just give it a push and let it go. I want to calculate the velocity of the rod as a function of time. So let's do that. And you know, because it's the same setup, if I just give the rod a push and let it go, the force on the rod is going to be to the left, right?
Mm-hmm.
Okay. So let me draw my picture here. And right now I'm only concerned about this side. I don't care about the other side because the flux is changing through here. Okay. And I can make this side open, so then I don't have to worry about, for sure I don't even worry about this side. Let me draw the fields into the board. It's uniform. I don't want to keep drawing X's. Okay. So the field's into the board. V is to the right. And what do we know? We've already established that there will be a force on the rod at the left. So we know okay, we know that. And we know that its value is going to be this. And in fact, let me put the sign in. So it's, let me say to this, that's a negative x direction. Let me be careful with signs now. Because I want to find v as a function of time. And this is the net force, right? There's no other force on the rod in the horizontal direction. Let's pretend there's no friction between the rail and the rod. Assume no sliding friction. And so this is going to be equal to MA. But A is dV dt. So I have m dv dt, and this is the motional current, which is delta v over the resistance of that circuit times L times B. But delta V we already established. And again, I should use script V. This is just going to be minus B L V It look okay so far? This is basically a differential equation, but it's separable. It's probably one that you do in Calc 2. So I'm going to put all the V's on one side, all the T's on the other. And then integrate. So when I integrate this, let's see. The left side gives me natural log. The right side is going to give me plus some sort of constant of integration. And guess what I'm going to do next?
Exponential.
Okay, so let's exponentiate. What do we get? So I'm going to get V equals e to the c, and I'll just write it like this for now. E to the c times e to the minus b squared L squared over mRt. And usually I still call this a c, but students object to it. So e to the c is just a constant, right?
Mm-hmm.
I just call it k. I'll make a capital K maybe. Physicists will still call it c, but mathematicians don't like that because we don't care, just a constant. What is K? What in the world is K?
It's the initial condition.
It's what?
The initial condition.
So initially it was going against some initial velocity, right? So because at t equals 0, when t equals 0, what's this exponent?
1.
One,
Or just the whole thing.
the whole thing is 1, right? So the velocity has to be equal to the initial velocity. So this is going to be equal to v rod initial, and then e to the minus b squared L squared t over mr. And so as t goes to infinity, what happens to the velocity of the rod?
0.
It goes to 0. So this is what I was talking about earlier this morning. And eventually, if you just give it a shove, eventually, and you don't apply a force on it, it's just going to come to a stop. Although this says it's going to come to a stop in an infinite amount of time, it really doesn't, because there's friction in the system, which we didn't account for. Okay. So I'm going to do another example. Any questions on this one? Okay. So I do have a little mistake in my picture in this problem. The right-hand side should be open. Okay. So this is a rail gun. So in this particular problem, I have a power supply. So let's change this. And let's pretend I have a special power supply that will maintain constant current. Okay, no, power supplies won't all do that. Let's say we have a very well regulated power supply so that as this thing goes to the right, the current delivered by the power supply stays constant. I want to write down the velocity as a function of time. And again, the right end should be open. My picture's wrong, okay? The right end of that thing should be open, because otherwise I have to consider the other loop too. Now, first of all, I know that my answer is probably going to have some sort of exponential because this one did. I know that as this rod accelerates because of the battery, what's going to happen as this accelerates? As the speed of the rod increases, this is going to get bigger. And probably at some point, this motional EMF is going to be just as big as the current in my circuit. And my total force will be zero, and this thing will actually end up going to get some constant velocity. So this thing can reach terminal velocity. Now, realize that this problem is idealized because you got to take into account your power supplies, how well they're made, etc., and the heating that goes in the rod, in the rail and the rod. Okay, so if you're trying to design a rail gun, there's more things to it than what I'm just doing here. I'm ignoring the heating effects. Okay, that's a rail gun, though, right?
Yeah, they just have a really, really big power supply.
Yeah, you need a very big power supply. You need to take into account the fact that everything's going to get warmed up. Okay. We still know, there's going to be a force on the rod to the left and a force to the rod on the rod to the right. And that's due to the power supply. So what's going to happen is I close the switch. You're going to have current go counterclockwise, right? I'm sorry, clockwise. So you're going to have current going this way. As this thing accelerates, you're going to have an induced current in the opposite direction. Or motional, however you want to call it. And they're going to counteract each other, so the total current is going to be the sum of these two. Or however you want to write the sum or the difference. So the force on the rod is going to be a little bit different. The force on the rod is going to be different because my total current, and they should call it motional, not induced, just to be consistent. Is going to be I minus I motional. That's my total force on the rod. And at the beginning, the force is going to be to the right. So this thing is positive. And so A is dV dt. Now, let's write the power supply voltage. How should we write it? I'm trying to use this as, let me just write it as V sub S. It should be delta V sub S, but I'll write it as V sub S because I don't have to write as much. I'm being lazy. Okay? Is this okay so far? It's the same equation as before, right?
Mhm.
Well, what's the current? What's this current equal to?
V sub S over R.
Okay. What's this one equal to? So I can factor out the R, right? So I'm gonna write it like this. And now what I'm going to do, I'm going to put all the terms with the V on one side and all the terms with the dt on the other. So I'm going to get the following. And to make life easier myself, I'm going to switch this around and put a minus sign out here.
Hey, Professor, isn't the current on the positive one, isn't that time dependent? Didn't you say the current's going to increase as it moves further away?
Why is that current time dependent?
Just because, like, as the rod moves to the right, the source is going to supply. It has to supply more current to keep it constant, right? Or no?
Well, I just want to make sure that the power supply current is constant, not the current in the whole circuit.
Right. Okay.
So I is going to stay, it's a well-regulated power supply, so I stays constant. I have the power supply stays constant. So if it's designed to put out 10 amps, it'll always put out 10 amps.
Right.
Okay.
I misunderstood what that meant. I thought it meant that it would keep the current across the whole circuit constant.
No, I don't want to do that. Yeah, that's fine. So what am I going to do next? I'm going to integrate this thing. If I integrate both sides, what am I going to get? I'm going to get and then what I'm going to do.
Multiply by BL.
Okay, let's multiply by BL. I don't want to rewrite everything. Okay, this is a constant, okay? I'm not going to put a BL here. You might not like that, but, right? It's a constant. For a physicist, I don't care. I don't care about the BL there.
You can write C1.
All right. Okay, I know the math people don't like that. So now we exponentiate, right? Oh, I'll write e to the C1. And then let's see, what else can we do? Let's solve for v. Let's solve for little v. If I solve for a little, oh, by the way, before I do that, let me rewrite this. And let's solve for v, little v. Make sure, just let me know if you can't see anything. What's K? Anybody know what K should be?
Is it minus V?
Yeah, isn't K, why is K minus V?
At t equals 0, it is. I did something.
What's V at t equals 0? It started from rest, right?
Yes.
So that means that V can be written this way. And what happens at t equals infinity?
It reaches certain speed.
Yeah. Which I call terminal velocity. Now, I actually don't have to do all that work to figure out the terminal velocity. Okay? Because I know when I reach terminal velocity, what's the acceleration?
0.
0. So basically, I set this thing equal to 0 and solve for the velocity. All right? To find the terminal velocity, I just need to set this equal to 0 and find it. I should get that same expression. Okay? This is from your book. This is a problem in your book. It's one of the red quoted problems from your book because it's considered a little bit more challenging. But it's really more the math that's challenging. Okay. Let me check the time. So briefly, there's a lot of applications of the ideas that we're covering in this chapter. Induction heating on stoves. One can spend a lot of time talking about the applications. So some stoves are use induction heating. Of course, if you have an induction stove, you can only use certain pots. You don't want to use ceramic pot on an induction stove. You need something metal. Magnetic recording, tasers, electropneumatic valves, coin mechanism vending machines, SIDS monitors, GFCI protection. I mean, the list is on and on. The applications for the topics in this chapter are just so numerous. I mean, the braking system we talked about, which is cool, or the regenerative power that you see in the electric cars. I mean, it's incredible the amount of applications of these ideas. Okay. Here's one example. It's called the electric guitar pickup. So your guitar string is steel, but it's magnetized. It's magnetized because, and I'll blow up the picture. It's near a magnet. So when you put something magnetic next to a magnet, it becomes magnetized. It acts like a magnet. When you pluck the string, you have a vibrating magnetic field. So the flux through that pickup coil changes. It picks up the signal. The signal's not very big, so you have to electronically amplify it. So there's another example. So I think the last thing, and I'll do some demos next time on Tuesday, the last thing I want to consider is taking a loop of wire in a magnetic field and rotating it. So let's say I take a wire in a magnetic field and I rotate it. What do you think is going to happen? Let's pretend the magnetic field is uniform just for the sake of making the math simple. Okay, so let's take a look at this. So I have a loop of wire in a magnetic field, and I'm just going to rotate it. Let's say I rotate it at some constant rate. So if I rotate it at a constant rate, what happens to the angle between the magnetic field and the normal to the loop? So I have a loop of wire. I have a magnetic field that points this way. And I rotate the loop of wire so that the normal changes direction. So it's one point is like this, and then at some other time, the loop of wire is like this. And so the normal to the loop now is like this. And what I want to do is calculate the induced EMF. Let's do this for one loop. Let's say we just have one loop of wire. So I want to calculate minus d phi dt. Let me use a better marker. But the angle between these two constantly changes. We're rotating at a constant rate. So rotate loop. Okay. So this is not just one, it constantly changes with time. So basically, and again, we're saying the magnetic field is uniform. So the angle between these two constantly change with time. I'm gonna write it like this. Oops. If theta varies with time, if the angle changes with time, can I write the angle as a function of time? For those of you who've studied rotational motion, if the angle varies constantly with time, how do I write the angle? How do I write the angle? Can you just write it? I'm sorry?
Is it omega dt?
Yeah, so if d theta dt is omega, then theta is omega times time. So then my induced EMF but we're assuming B is uniform, so this integral is easy because I can pull these two out, and I'm going to get the following. And we're just going to integrate over dA. What's the derivative of cosine omega t? Derivative of cosine of sine? The answer is yes. That's the induced EMF. But this is for one loop. If I have many loops, for n loops, in other words, if I just wind a coil with n loops, then E is equal to, oops, the minus sign is gone. The derivative of cosine is minus the sine. And a device that does this is called what? It's a generator. This is an AC. This is the physics for the AC generator. The AC generator in general. Right. This is the generator equation. You can generate voltage. So I do have a generator here. I'm going to rotate a coil in a magnetic field. Right, when I rotate it, light goes on. I'll bring the other generator next time. Okay? So I'm generating a voltage. That's the equation. What's coming out of your outlet in your homes, I gotta be careful. What's coming out of most of your outlet in your homes is the following. What you're getting in your homes is this. Again, this is most outlets, not all of them. That's what's coming out of your outlet. Okay, some generator is producing this voltage. Now, granted, the generator at the power plant produces a larger voltage, but you use transformers to step up the voltage and step down the voltage so that you get this coming into your house, at least into your outlets. There are some outlets where this value is like double. This amplitude is double. Okay. So this represents what comes in your home. So this is another huge idea that comes out of Faraday's law, is that we can generate electricity and develop a power grid so that we can deliver energy to our homes. And so what happens is the energy's delivered at the power plant, the energy is produced at the power plant. It is stepped up with transformers to high voltages, and the reason why you do that is if you step up to high voltages, you have lower current. You have less energy loss because you're delivering energy over a long wire. And then as you get closer to your home, everything stepped down. Whoops. Everything gets stepped down. And so in your home, you either get 240 or 120. Okay. There's more to it. Okay, there's more to it than what I've said, but that's just the gist of it. Questions on that? And it did skip the equation. I'm sorry, I wasn't displaying.
Can we use an AC generator for a DC motor?
You want to use an AC generator for a DC motor?
Yeah, like can we use it?
No, because the AC current switches, right? So you want an AC generator for AC motor, because right, the AC generator changes sign every half a cycle.
So can we use it if we take out the commutator?
You'd have to split it. I mean, you'd have to have two. You'd have to have two conductors. So let me see if I can show you. This thing is so heavy. I don't want to use my other camera, so. So when I show you this one, I would use these two separate ones, one for the positive, one for the negative for AC. Okay, and then you would do it. But we're trying to, for the purpose of this project, this is supposed to be a DC motor.
No, I was just asking because it was like a generator, so maybe it can supply the power to it.
Yeah, you can.
Yeah, I'm not going to use it. I was just asking.
Okay. No, yeah, you can do it, right? In fact, next time what I'll do, I'll play around with it. It's hard to demonstrate that one as an AC generator because I need a giant multimeter, which I don't want to bring here. What I might have to do is spin it by hand and connect it to a voltmeter and just show the voltmeter. But I usually have a real old-fashioned needle one that's giant. And when I spin it, you can see the needle move. It's not a very, it doesn't produce a lot of energy, but at least you get to see how a generator works. Okay. I mean, this generator is designed to produce enough voltage so I can turn this light on. So, and there's some other interesting things I want to add to this on Tuesday. So on Tuesday, what I'm going to do, I'm going to finish up talking about the applications, and then I'm going to talk about the displacement current, which will take me about 35 minutes, hopefully. And so I will have time to give you some polling questions. So I'm going to actually do a poll. I was going to do it today, but then I changed my mind. I'm going to give you some polling questions so you can just try to see how you're doing with this material. If you want, I can give, and if I have a lot of time left, I can give you. I have questions even for the chapters 28. I'm sorry, for chapters 29 and 30. Okay, so I can give you a lot of polling questions on Tuesday. I want to use that time to ask you guys questions. And I don't want to start the new unit until Thursday. Okay, I just want to keep on track. I don't want to be too far ahead. Because I'm a little bit ahead now.
And that unit will not be on the exam, right?
I'm sorry?
That new unit will not be on the exam.
Well, I won't start the new unit, that's chapter 32. So that won't be on the exam, just 29 through 31. So the last exam will be chapters 32, 33, and whatever I get through 34, which I don't cover in much depth. I kind of just blow through it because 34 is just equation driven. Okay, so I'm going to use time. Hopefully, I can use a little bit more than half the time to lecture, and then the other half maybe to answer questions you have on this unit. It's nice to be a little bit ahead because what I like to do is ask polling questions so you get to see where you guys stand. This is the first time in a long time I've been able to do that. Okay. So, do you guys have questions on the homework?
I do.
Okay, go ahead.
I was wondering if you could, like, maybe work a little on number 16. I tried it, but nothing came of it.
What did you try?
So I treated the figure as like a one long wire without holes, and then I just subtracted like two smaller wires that are basically the holes.
And it wasn't working.
Yeah, I know that. I know the two holes have different currents, and I tried to figure that out.
Okay. So you first use Ampere's law, and you're trying to find the field at P2.
I was doing P1.
Oh, P1, okay. So let me draw the picture. So the first thing I would do is draw the solid one. It's uniform density, right? Yeah, it's uniform. That makes it a little bit easier. So the total current's I. The current density let's assume you have this whole thing with current I. And you want to find the field at this point P, which is how far away? Oh, so this is R away, okay. So you're outside this, so you want to use Ampere's law. Again, whether you write S or L doesn't matter. I'm going to write the current this way. Is that what you did?
Not for the bigger circle. I did for the smaller circles. I thought the current was just I for the big circle.
Yeah, you're right. But I mean, in general, it's going to be like this, though, right?
Yeah.
I mean, when you integrate over the whole thing, you get I. So the big one is going to give you, and where's the current here? It's out of the board, right? Yeah, it's out of the board. So the field due to this big one's to the left, right?
Yeah.
Okay, so the first one is going to give you a field to the left. It's going to be this. We can put the unit vector later.
Why is it negative? Oh, you're just doing direction right there?
Yeah, right, that one's to the left. Now the other ones are going to be to the right because they're holes. Isn't that true? They act like
I don't know. I just
right.
I thought it'd be no. Sorry.
I mean, you got to
I just
treat this as a hole. A current going in the opposite direction. So this is going to produce something that way.
I kind of did it like that. I just subtracted it off anyway because they're just holes in it, so they're not really contributing to anything really. So I just subtracted them off.
So without, how much area is this compared to the whole thing?
Isn't it like pi r squared over the bigger radius pi r squared?
No, the big
Is that what you
radius.
mean?
The big radius is 2a, right?
Yeah, it's 2a.
This is 2a. This is a, right?
Oh wait, I think it's actually a, and then the other one's a over 2.
Yeah, it's A and A over 2.
Oh, sorry. How much area is this compared to the big thing?
It should be, what I wrote was pi a over 2 squared over pi a squared.
Which is?
Just 1 over 4 is what I got.
It's 1/4, right? This area is 1/4 this area, right?
Yeah.
And the current density is the same, right?
Yeah.
So this carries 1/4 the current of the whole solid thing, right?
Yeah.
Okay, so then I have let me do it this way. The only thing, the distance is from here to here, right?
And so it's 8 pi, right?
Yeah.
We multiplied by 4. Okay.
And then you gotta simplify it.
So the only thing with mine was the negative. There was my negative signs are on the other ones, and I have a positive on the first term.
Okay, so if you want the magnitude, then if you take the absolute value of what you have, you should get the same thing though, right?
Yeah.
Okay, because it wants the magnitude. So you got to write it as a positive number. You might have the term switched around. One of the terms switched around, so it's negative. I don't know.
Okay.
Right, your answer and my answer are negatives of each other, isn't that right?
Yeah.
So all you got to do is take the absolute value of your answer, and by what you can do is flip the order of the two quantities in the numerator around. If you have something like this, in the numerator, I mean, I don't know, did you get a common denominator on this thing?
No, I just put it in. I thought it'd be easier.
Yeah, you better get a common denominator, and the reason why is because I don't know how good the math processor is on WebAssign. It's not like Wolfram. Because here's how WebAssign was designed. It was designed it was put together at a college, and for many years it was run at the college, and graduate students really would put in the problems. and they probably hire some programmers to code the system. Then the publisher bought them out, and so they're probably using the same. The publisher probably didn't hire any programmers to modify it. They just hire programs to maintain it, and so they probably haven't changed a lot of it. They haven't changed the math processor for it. That's my guess. So you're probably going to want to find a common denominator here and simplify it. Okay?
Okay. Thank you.
Professor,
Yes.
for this problem, I did the same thing and I don't think it would mark it correct. So then I changed it, and I think what the question actually is saying is that the part of the wire that carries the current, that current is I, so the original current in the entire wire would be more than I. So the current density would actually be the current I divided by the area of the entire wire minus the areas of the two holes.
It's not phrased right, you're saying.
Yes,
Yeah,
and then
you're
it
right.
marked it correct.
Actually, you're correct in saying that, because I was looking at it as like, because I solved it differently from the way I thought about it, because I had my solution in front of me. It's like, wait a minute. So you're right. It is not properly stated. It should say what the current density is. Then you can do it. Then it makes sense. But you're right. The way it's stated is not correct.
Yeah, so the actual current the actual current through the entire wire would be more than I and not just I.
Yeah.
So I think then it would mark the answer correct, because then it did for me.
Yeah, because I treated it as the whole thing was I, right?
Yes.
Yeah. No, it is worded poorly. It should state the current density. So, so I'll email everybody. Just say assume the current is I for the solid cylinder of radius A.
So do the smaller circles, do they give a stronger magnetic field to that point?
Because it's closer, you mean?
I just mean than the bigger circle.
Well, yeah, it all depends on, because you have 1/4 the current, right?
Yeah.
It just depends on that distance, right? It depends on how small this distance is, because you're not given what R is, so it's hard to say. Because if R is really big, it's not gonna. I mean, it's not gonna be a bigger contribution. But if R is, if this difference is really small, then yeah, it makes a way bigger contribution than that one. So it just depends. Other questions? No other questions on the homework? 16 was the hard one, right? I can't remember. Did I give you guys a superposition problem with Gauss's law? It's been a while already. I thought I did. Or maybe not. But yeah, you can do problems like this with Gauss's law. So Jacob, you said you have a question on number 14 and 7. Let's look at 14. So number 14 is very similar to the problem I did in class last time? No, on Thursday. So you are using this equation in number 14. This is just going to give you B times 2 pi r. But then you're going to integrate your current density. I'm going to write it this way because everybody's exponent is different. And then your element of area is just 2 pi r dr. And it all depends on whether you're inside or outside. If you're inside, then you integrate from 0 to r and make these primes. If you're outside, then you integrate this to big R. So if you're inside, so for R greater than R, then you're going to get this. Solve for R. Solve for B. Okay. That's a quick way to describe that one. I just put N there, but your exponent will probably be different. Is that okay, Jacob, for that one? And number 7. So, Jacob, which part of number 7 are you having trouble with? Part B. So the two conductors are 3 millimeters apart, and they're both carrying, in my case, they're 9 amps. Okay? So if I draw a picture, I'm going to exaggerate the separation between them. So this separation is 0.003 meters. They've really exaggerated. They want everything relative to the center between them. And so, again, we're solving for the magnitude. So these are long wires. With currents in opposite direction. And so if you're standing here, this distance is 30.36 meters minus 0.0015 meters. I don't know if you can see the bottom one. This is 0.36 meters plus 0.0015 meters. And so I can call this R1 and this R2. Is that okay, Jacob? Yeah. Whatever your I is. I mean, you got to put in the value and get a numerical result, right? They want a number, and you got to express it in nanotesla. And then part C, you want the field to be 1/10 that of part B. And then solve for the location. So in part C, this number is unknown, this number is unknown, and this number is 1/10 of the one in part B. Other questions? Is homework assignment going okay? This might be out of the three the hardest one, I think. I mean, the chapter 31 homework, there might be one or two problems that are hard, but I think this one has the hardest problems. So if you're doing Chase, if you're using a lot of submissions on a problem, just send me an email, because I don't want you to just spend your time working on a problem and keep getting it wrong. It could be a simple issue. Of course, when we're on campus, you can just come to my office right away, and it's a little bit easier when you're on campus to ask me those kind of questions. But yeah, if you do a problem 4 or 5 times, then you probably want to email me or the tutor, or just try to get some help. Or just go on Discord. Other questions?
Yeah, I just have 3 problems, and
almost done?
there's that one that wasn't accepting it.
Okay. Yeah, that was weird, because I saw the code for it. It didn't make sense. Because there was another one I kept hitting, I kept refreshing the screen, and there was one where the currents added up to 0 and it gave the answer of 0. But for yours, it didn't work, and I have no idea why. And all the values were to 1 decimal place. So I just don't understand why that one combination of I1s, I2s, and I3s don't work. It just didn't make sense. Okay, so if you guys don't have any more questions, I'm going to end it here. If you're having trouble with your motor, if it's not working, send me a video, and hope I can get. I'll find some time to look at it and give you a response. Okay. I mean, hopefully, I can see from the video. Obviously, it's a lot easier in person to see the problems, but I'll do what I can. Okay. If it's not working at all. If it is working and you're trying to get a lower voltage, look at the discussion board. All right, you all have a good weekend.